Hello physics students. Today we're going to continue talking about the concepts in Chapter 2. We already started talking about the concept of displacement. Today we're going to start talking about scalars, vectors, speed, and velocity. So let's go back to what we were talking about in the previous video about displacement. What we said about displacement is that it could be calculated according to the equation delta x equals x final minus x initial. In other words, the change in horizontal position of an object is going to be its final position minus its initial position. We then went on to say that you could calculate the change in position for an object by taking its final position, which in this case is 84 centimeters, its initial position, which in this case is 24 centimeters, and simply using the equation to calculate the displacement. By making it a positive number, we're indicating that the gecko ends up 60 centimeters to the right of its origin, or in this case, the point of reference would be 0. It ends up 84 centimeters to the right of the point of reference because it started out 24 centimeters to the right of the point of reference. But its total displacement from its origin is 60 centimeters to the right. Now, what's important to understand is that this quantity, displacement, is what we call a vector quantity. What makes it a vector? Well, its displacement indicates a magnitude and a direction. The magnitude is simply a number. How far did it travel? So the amount usually answers the question how far or how long or how much. So in this case the displacement is 60. The magnitude of the displacement is 60. But it also includes a direction. In this case the positive indicates that we're talking about to the right, up, or forward. Since we're dealing with the variable x, indicating horizontal motion, this means it ended up to the right. What makes it a a vector quantity is because it indicates both a magnitude, some number, and a direction, either a sign or a direction given in words. So displacement would be an example of a vector quantity. Distance, on the other hand, is what we call a scalar quantity because it indicates magnitude only. Imagine that this gecko returned to its starting point. That is, it traveled 60 centimeters to the right, stopped, and went back to the place it started. Its displacement would be 0 centimeters because its final position would be 24 and its initial position would be at 24 centimeters. So it would have no displacement whatsoever. However, what distance would it have traveled? It would have traveled a total of 120 centimeters because it would have moved 60 centimeters to the right and then 60 centimeters to the left. Distance is a good example of a scalar quantity because when we say that it traveled 120 centimeters, 120 centimeters has a magnitude and a unit, but does not indicate direction in any way. That's the difference between distance and displacement. One is a vector quantity, the other is a scalar. I want to introduce you to another example of vector and scalar quantities when we take a look at the difference between speed and velocity. Speed is a scalar quantity. Speed indicates only a magnitude. Speed will never include a direction. If you're traveling down the road at 55 miles an hour, that's your speed. Velocity, on the other hand, is a speed that includes includes a direction. So if you're traveling on Interstate 77 at 55 miles an hour and you're heading north, that's a velocity. If you're traveling on Interstate 77 at 55 miles an hour and you're heading south, that's also a velocity. But if you're just traveling at 55 miles an hour and no indication is made of the direction, you've given me a speed, a scalar quantity including only magnitude, not a velocity. Which of the following shows speed and which shows velocity? I traveled here at a rate of 16 meters per second. I traveled from the north at a rate of 16 meters per second. Because the north is a direction, this is a vector of velocity. This is scalar. It's a speed. I'd like to take this opportunity to point out that both speed and velocity are what we call a rate. That is, we're comparing one physics quantity, something that can be measured with a number, like distance or displacement, to time. When we compare our distance over a certain amount of time, we get a speed. Notice that distance and speed are both scalar. When we compare our displacement over time, both vectors, displacement is a vector, we get velocity, which is also a vector. Now, as it turns out, there are different flavors of speed and velocity. We want to make sure that you understand the difference between these distinctions between these different flavors. So the first one we want to talk about is average velocity. Well, what does this mean? Well, velocity itself is when we measure the change in position of an object on a certain number line over time. What makes it an average velocity is that we're usually talking about a long time interval. Now, this is sort of subjective, but what we mean is a long enough time interval that it's not a split second. It's not a specific instant in time. It's 2 instants in time. It's a long enough time interval that we can say, here's the beginning of that time, and here's the end of that time. It's not such a short amount of time that it happens so quickly that it's an instant. So when we're dealing with velocity, we recognize that we are paying attention to a displacement, all right, a change in position over time. So that means our average velocity is going to be indicated with a letter V and a line over it, and it's going to be a change in position over time. Now, because I've indicated that this is horizontal position, it's customary to add the subscript x to indicate that we're talking about an average velocity that's horizontal. We also could have said that the average velocity moving up and down was measured, or the average velocity moving forward and back was measured. These are all acceptable versions of average velocity. So what variables are we dealing with? Well, we already know that delta means change in, and x means horizontal position. So this is displacement. And then we've introduced delta t, a change in time, or something known as a time interval. And then finally, this is your average velocity. All right, because this takes a certain amount of time, because the average velocity requires a time interval, that means it can be graphed. That means we can look at a starting position, we can look at an ending position, and then we can compare that to how much time it took to get from that starting position to that ending position, and graph it or create an equation that describes its motion. So here we can see a graph of the known position of an object at specific times along its path. Please note that it could be moving along the x-axis, which would be left and right motion, the y-axis, which is vertical motion, up and down, or it could be moving forward and back. Our graph doesn't indicate that, but we can see here mathematically the y-axis indicates the position. It could be its horizontal, vertical, or linear position forward and back. The x-axis indicates time. What does the slope of this graph indicate? Well, here we can see that at time 0, it had an initial position. After 4 seconds, it had a final position. So this gives us our change in position, and this gives us our change in time, because here we have our initial time, here we have our final time. That means the slope of the graph, the rise over the run, must be our average velocity. So please note that the slope of any position time graph is going to give you average velocity. Based on that, we can indicate that no slope would mean no velocity. A really steep slope would mean a large velocity, and a fairly shallow slope would be a pretty low velocity. Also, pay attention to the direction of the slope. A positive slope would mean a positive direction, which could mean to the right, up, or forward. A negative slope would mean a negative direction. If you take a look at these, you can see here that object 1 has a pretty large positive slope. So it has a large positive average velocity. In other words, it's moving pretty fast, and it's moving to the right. Object 2 has no slope, which means it has no velocity. Object 3 has a pretty shallow negative velocity, which means it's moving in a negative direction, left, down, or backward, but it's not moving very quickly relative to object number 1. Now please notice the difference between instantaneous velocity and average velocity. If I said, hey, I was driving down the highway and sometimes I was moving as slow as 55 miles an hour, and at other times I was going as fast as 75 miles an hour, and so I said, hey, I traveled 100 miles and I did it in 2 hours, well then my average velocity is 50 miles an hour. My change in position was 100 miles, my time was 2 hours, so 100 divided by 2 is 50 miles an hour on average. But I just told you, there were some times I was going as slow as 55, and then sometimes I was going as fast as 75. There must have been some other times in there when I stopped or was below 55, otherwise my average wouldn't be so low. But my point is that if you wanted to know how fast I was going at any specific instant, this would be known as my instantaneous velocity. It's the velocity at a specific point in time. So here you can see it's determined by the slope at one point in time. So although I may start at 0 and end at 30, and the average velocity may be one thing, at this specific moment, you can see that my speed is a little faster. So my instantaneous velocity is my velocity at a very specific time. At 3 seconds, I was going 12 meters per second, although I'm quite certain my average velocity during that time was something else.